Welcome to the deep dive. Today we're looking at something really fascinating, a tech breakthrough that's genuinely changing what wearable tech could mean. We're talking displays so small they practically disappear.
That's right. It's coming out of the Julius Maximilians Universität Würzburg, JMU. Physicists there have managed to create what seems to be the world's smallest, most precise light-emitting pixel. It's quite remarkable.
So our mission for you today, our listeners, is really to unpack this. We want to get into the core physics challenge that made this kind of miniaturization seem impossible for so long, and then how the JMU team actually engineered a fix for that fundamental problem.
Yeah, what the trick was.
Exactly. And ultimately, what does creating a pixel this incredibly tiny actually mean for things like AR glasses, future optics?
And it's important to stress this isn't just like a small step forward. We're talking about overcoming a really major, long-standing physical barrier. It's about how you get light out efficiently at that tiny, tiny scale.
Nanometer scale, right.
Exactly. Taking components that were already small and pushing them way down into the nanometer range. We're talking a millionth of a millimeter. It's hard to even picture.
That scale reduction just sounds, almost abstract. So let's try and ground it. Let's unpack this. What's the actual, game-changing number here? What measurement really shows how big a leap this is?
Okay, the key is the size they hit while keeping the brightness up. The project leaders, Professors Jens Flom and Bert Hecht, they successfully made an orange light pixel that measures just 300 by 300 nanometers.
300 by 300 nanometers.
Yeah.
Okay. That sounds tiny, obviously, but how does it stack up against the tech we have in our phones or TVs right now?
Well, that's really the kicker. This microscopic pixel, it's just as bright as a standard OLED pixel, the kind we find in high-end displays today.
Okay, same brightness.
But, and this is the big difference, a conventional OLED pixel is around 5 by 5 micrometers.
Oh, okay. Micrometers versus nanometers. That's not even close.
Yeah. Not at all. It's a huge difference. To put it in perspective for you, the listener, shrinking from 5 micrometers squared down to 300 nanometers squared. That's a reduction in the actual light-emitting area of nearly 300 times.
300 times smaller area.
While putting out the same amount of light. That's the efficiency gain through sheer scale reduction. It's pretty impressive.
That reduction is just, staggering. And I guess when you shrink something by 300 times, the applications become pretty clear, pretty fast.
Absolutely. They did the math. You could fit a full high-definition display 1920 by 1080 pixels onto an area of just 1 square millimeter.
1 square millimeter. Seriously, HD resolution fitting easily on the head of a pin.
That's the idea. And that is the kind of integration density that the AR and VR industry has been, dreaming about, frankly.
Right, because that means the whole display system, the projector part, could actually be built right into, say, the arms of a pair of glasses.
Exactly. Built into the frame, projecting light onto the lenses themselves. It could finally make smart glasses look less like, clunky tech gadgets and more like actual glasses, sleek ones.
Okay, but getting there wasn't just about building smaller manufacturing tools, right? You mentioned this is based on OLEDs, organic light-emitting diodes. We know those.
The basic concept is similar. Ultra-thin organic layers sandwiched between electrodes. Current flows excites molecules. They emit light.
Yeah, OLEDs give us those great deep blacks, vivid colors, good energy use, because there's no backlight needed. That part's established.
Correct. OLEDs work great at the usual scale. But the big question for the JMU team was, why couldn't we just shrink the whole existing setup, just make everything proportionally smaller?
Yeah, what stops that?
And what's really interesting is that the bottleneck wasn't just manufacturing limits. It's a deep physics problem. It's about how electrical current behaves when you shrink down the metal contacts to that tiny scale.
So it's not the organic layers, it's the metal contacts.
Yeah.
The electrodes.
So specifically, the tiny metallic contact that acts as the electrode at this scale. They called it a gold antenna. And the analogy they used is perfect. It acts like a tiny lightning rod.
A lightning rod. Okay, how so?
Well, instead of the current spreading out nicely and evenly across the surface, which is what you want for stable light emission,
Right.
when you force that metal structure down to 300 by 300 nanometers, the current and the electric fields it creates, they don't flow evenly. They bunch up, they concentrate and emit mainly from the microscopic edges and corners of that tiny gold antenna.
Ah, okay. Like static discharge from a sharp point.
Exactly like that. And what happens at those supercharged corners where the field is intense?
That sounds like it would be bad.
It's catastrophic for the pixel. The electric forces become so strong they actually make the gold atoms mobile.
the gold atoms start moving around. Gold is usually pretty stable stuff.
Right. But the forces are just that concentrated. Think about it. Electrical forces focused on a corner, maybe just a few hundred atoms wide, making solid gold atoms migrate.
Wow. I would not have expected that. Moving gold atoms.
And these migrating gold atoms start forming tiny conductive threads, what the researchers called filaments.
Filaments. Like little wires?
Sort of. Conductive pathways made of gold that gradually grow through the organic, light-emitting material.
Oh, I see where this is going.
Yeah, they grow until they connect the top and bottom electrodes. Bang. Short circuit. The pixel is dead.
So that instability, that filament formation, that was the core physical problem, stopping nanoscale OLEDs from working reliably.
That was the main roadblock. Overcoming that was key to getting any kind of stable operation at this scale.
Okay, so if the problem is these supercharged corners and edges causing gold atoms to move and create short circuits, how on earth did the JMU team fix that? Engineering something at that scale seems incredibly difficult.
Well, this is where the solution is really quite clever, almost elegant in its simplicity. They didn't actually change the gold antenna itself.
No, what do they do then?
They added a new component, a specially made insulation layer placed right on top of the antenna.
An insulation layer. Okay, so like putting tape over the problematic bits.
Kind of, but very precisely engineered tape. They place this layer over the gold antenna, but crucially, it's not solid. It has a perfectly circular hole right in the middle.
A hole?
Yes, a tiny opening, only 200 nanometers in diameter, precisely centered over the stable part of the electrode.
Wait, let me get this straight. They basically put a tiny mask over the electrode, covering up those destructive corners and edges.
Exactly.
And forcing the current to only go through that little 200 nanometer hole in the stable center.
That's the mechanism, precisely. The insulator physically blocks the current injection from those high-field problematic edges. It forces the current through the central area where the electric fields are much weaker, much more uniform, and far less destructive.
That actually sounds surprisingly straightforward for such a complex physics problem. Just block the bad parts, force current through the good part.
Simple in concept, maybe, but extremely difficult to manufacture at that scale. But yes, the principle is elegant. By keeping the current away from the corners, they removed the conditions that made the gold atoms mobile and formed those deadly filaments.
And did it work? Did it actually make the pixel stable?
It absolutely did. That structural change, that specific insulator with the central hole, was the key to reliable, long-lasting operation. As a proof of concept, their first nanopixels worked stably for 2 whole weeks.
2 weeks. Okay, that's a huge jump from instantly shorting out.
Exactly, even operating under normal ambient conditions. That demonstrated reliability is the massive breakthrough here, the proof that the concept is sound.
Okay, so the physics challenge of stability seems to be cracked, at least in principle. But connecting this to the bigger picture, where do they go from here? What are the next steps to get this amazing tech out of the lab and, maybe into something we could actually use?
Right, the researchers are pretty clear about that. There are 2 main hurdles left before this becomes commercially viable, you could say.
Okay, what are they?
First, efficiency. While the pixels are bright, the overall electrical to light conversion efficiency is currently quite low. It's around 1%.
1%.
Well,
Yeah, that's not great for battery life in a wearable device.
definitely not. That needs a significant boost for practical applications. They need to get much more light out for the power they put in.
Makes sense. And the second hurdle.
Well, it's pretty crucial for any display we'd recognize. They need the full spectrum of colors.
Right. The current breakthrough was just for orange light, you said.
Exactly. Orange is a good starting point to prove the physics, but for a real display, you need red, green, and blue. RGB. They need to adapt this nanostructure design to work efficiently across the full color gamut.
Okay, so boost efficiency, get full RGB color, if they can crack those 2.
Then the potential is enormous. This technology could lead to displays and projectors that are just unbelievably small, incredibly energy efficient, small enough to be integrated almost invisibly into things we wear.
We talked about eyeglass frames,
Right.
making smart glasses finally look normal.
That's the obvious first step. But the ultimate vision. Maybe even integrating displays like this directly into contact lenses.
Wow. High-definition displays in a contact lens. That's proper science fiction territory.
It feels like it, but this research validates that the fundamental physics for getting there might now be within reach. It shows a path towards displays that aren't devices we hold, but are just seamlessly part of our view of the world.
Yeah, projected right onto our vision.
Yeah.
And just for context for everyone listening, this work, detailing the whole failure mechanism and that clever installation fix, was published in Science Advances back in October 2025. So it's peer-reviewed, recognized as a major step forward in optics.
A significant global breakthrough.
So let's recap this deep dive. We've seen this incredible scale achievement HD resolution on just 1 square millimeter. Amazing.
Yeah.
We've understood the really tricky physics problem they solved, those migrating gold atoms causing filament short circuits.
The lightning rod effect at the nanoscale.
Right. And the elegant engineering fix. That specialized insulation layer with the tiny hole in the middle. This really lays the groundwork for, well, the next generation of genuinely wearable, maybe even invisible, AR and VR optics.
It really does. But it also raises a fascinating question, doesn't it? Something for you, the listener, to think about.
Oh, go on.
Well, if high-resolution screens can fit invisibly into eyeglass frames, or maybe even contact lenses, projecting information, graphics, whatever, directly onto our view of the world.
Yeah.
What happens then? What new ethical questions, what design challenges pop up when the line between the real world and the projected digital overlay just completely dissolves? When the whole world could become a seamless projection surface?
Huh. That's a really interesting thought. When the interface disappears entirely.
Exactly. Something to mull over as you watch this technology develop over the coming years. It's going to be quite a ride.
A compelling and slightly unsettling future vision. Well, thank you for joining us on this deep dive into the nano world and the future of how we might see things. Until next time, keep exploring the hidden structures shaping our future.